Okay, this is IB Chemistry. We are now talking about Topic 2, Atomic Structure, Section 2.1, the nuclear atom. A couple of big ideas from this unit are that the mass of the atom is concentrated in its tiny, positively charged nucleus. Another idea to think about in this topic from an international mindedness perspective is that isotopes are important. Isotope enrichment uses physical properties to separate isotopes of uranium and is employed by many countries as part of a nuclear energy and weaponry program. The United States, Russia, China, Iran right now is currently engaged in a nuclear weaponry or nuclear energy program, depending on who you talk to. So isotopes are very important. Another idea here, a theory of knowledge idea, is that atoms are super important to the basic building blocks of all matter. And in fact, the famous physicist, Richard Feynman, said famously, if all scientific knowledge were to be destroyed and only one sentence passed on to the next generation, I believe it is that all things are made of atoms. Another thing to keep in mind is that are the models and theories which scientists create accurate descriptions of the natural world, particularly when we talk about atoms, or are they primarily useful interpretations for prediction, explanation, and control of the natural world? That's certainly the case with atoms. No subatomic particle can or will be directly observed by your eyes, or mine for that matter. Which ways of knowing do you use to interpret indirect evidence gained through the use of technology? All of these ideas here might be helpful for you in your TOK class. Okay, what do we need to know about atomic structure? Atoms, like I said, atoms contain a positively charged, dense nucleus composed of protons and neutrons, also called nucleons. The electrons are negatively charged, and they occupy the space outside the nucleus in energy levels, as we see here from this picture. So let's talk about the structure of the atom. That's really what this section is about. What is the atom made of? Protons, neutrons, and electrons. And I know some of you are saying, well, there's also quarks and bosons and muons. That's true, but we're going to focus on these particles right here. Here's a picture of the atom. It's a Bohr model of the atom, which we'll talk about in a few slides. This is not to scale. Electrons are much, much farther away from the nucleus, and the nucleus is, like we said before, extremely small. Most of the atom, all matter, is empty space. So that's something else to keep in mind. The nucleus, as we've said already, is extremely dense. That's where all the mass of the atom is. Okay, well, let's talk about particles. We know a little bit about particles from the previous unit. Elements, well, they are substances that cannot be broken down into simpler substances by a chemical reaction. So gold is an element, sodium, oxygen. Atoms, they are the smallest particle species of an element that retains the properties of that element. So if you split an atom, it's no longer an atom, it's a collection of subatomic particles. A compound, well, that's a combination of two or more elements. And there are different flavors of compounds, which we'll learn about in topic 4. A molecular compound, which is two nonmetals sharing electrons, and an ionic compound, one metal and one nonmetal, where electrons are transferred. Let's talk for a few moments about the models of the atom. This is actually not testable material right here, the next couple slides, but it's kind of important to set up what we're going to talk about in subsequent slides. So, plus it's also really interesting stuff. John Dalton. Dalton's atomic theory led to J.J. Thomson's plum pudding model and the discovery of the electron. Dalton's work occurred in the mid to late 1800s. J.J. Thomson about 10 years after that. Ernest Rutherford in the early 1900s, with his famous gold foil experiment, discovered the proton and the nucleus. Niels Bohr refined Rutherford's model, which was a refinement of J.J. Thomson's model. Niels Bohr's model, which you often see in textbooks and other examples of atoms, is a solar system model where the electrons orbit around the nucleus. Lastly, and the model that's in favor today is what's called the quantum mechanical model. And it's a model based on electrons existing in cloud shapes or orbitals. None of these models are accurate totally 100%, but they're very useful for helping us describe ideas. Okay, let's talk for a second about Dalton's atomic theory. He had about 5 different tenets. One is that all elements are composed of atoms. Each element has atoms that are different from other atoms. Atoms cannot be divided, subdivided, or destroyed. Atoms of different elements combine in simple ratios to form chemical compounds. And lastly, one type of atom cannot be changed into another type of atom by a chemical reaction. So this was like, the 1870s when Dalton was proposing these things. Pretty impressive. We know now that not all aspects of Dalton's theory proved to be correct. For example, we can divide atoms. Atoms can have different masses, isotopes. But some important parts are still relevant. All matter is composed of atoms. Atoms of one element differ in properties from those of other elements. That's important. Okay, well, J.J. Thomson's model, sometimes called the plum pudding model, J.J. Thomson discovered the electron with its negative charge. He adapted the Dalton model to display negative electrons suspended in this positive fluid. They knew that the atom was neutral. So if he found electrons, there had to be something positive floating around there too. And so that was the fluid, this positive gooey stuff. The negative electron held in place. To me, it looks more like a chocolate chip cookie. It's also called a plum pudding model. Plum pudding was popular in the day of J.J. Thomson. It's kind of like oatmeal with plums in it. So think of the oatmeal as the positive, the plums as the negative, the electrons. Now, Rutherford's model. Rutherford discovered the positively charged dense nucleus. Beautiful experiment, the gold foil experiment. He discovered that that's where most of the mass of the atom is. Electrons surrounded the nucleus. Most of the atom was empty space, and he figured that out. Didn't know anything about energy levels. So here's Rutherford's model of the atom. Notice that it's got, again, not to scale, but the positive area of the atom is in the center, and it's denser than it was in the plum pudding model. He still has these negative plums or raisins or chocolate chips floating around. And most of the atom is empty space. There's a problem with Rutherford's model that we're not going to go into too much, but it's worth mentioning. What do positives and negatives do? Yeah, they attract each other. So in this model, why don't the electrons just fly into the nucleus? That was a big problem. Bohr had a solution. Maybe not a perfect solution, but a solution. Instead, the electrons just hanging around the nucleus, which would lead them to crash in, maybe the electrons themselves had energy and maybe they orbited the nucleus like planets in the sun. So this is the first sort of Bohr model and something that was popular for a while. The one on the right is a more refined version that shows the orbitals of the electrons in fixed spaces. Bohr came up with this idea that led to the size of the electron's orbit. Bohr came up with the idea that the size of an electron's orbit was somehow related to how much energy the electron had. He was onto something. The energy level of an electron was determined by how far away from the nucleus it would be. So if we're looking at this more refined version of the Bohr model, we see that electrons live only in certain energy levels or only in certain locations outside the nucleus. And the further they are from the nucleus, the higher they are in energy. So the movement of electrons is related to light and energy. See, how can you kind of think of the Bohr model? Think of it as stair steps or a ladder. You can't stand between the steps on a ladder, and the electrons can't hang out between energy levels. Number the energy levels 1, 2, 3, 4, and now you're starting to put together a model of the atom that makes sense with what we observe. Energy levels in an atom are different from the steps on a ladder because they are not evenly spaced. Well, what do we mean? Well, here's a regular ladder, nice, normal, evenly spaced steps. Here are the energy levels on an atom. And important to note, the jump between the ground level and the first energy level. It's a big jump. And then as you move away, these energy levels get further and further, or excuse me, they converge and get closer and closer together. And as you go up in energy on, as you go up a ladder, you go up in energy. As you go out, let me go back, whoopsie. So as you go out from the nucleus, you're going up the ladder or down the periodic table. Okay. The last and most current model is the quantum mechanical model. Now we know that electrons do not follow paths around a nucleus. That's just would be too convenient. Instead, the current understanding is that they pop in and out of existence so fast it's crazy. So imagine the flash on your cell phone camera. That's what an electron does. It pops in and out of existence, literally. Quantum mechanics is used to explain this kind of crazy behavior, and it's based on probabilities. There's a good probability of finding an electron in a particular location, but the electron can be anywhere at any time, and it can even be in more than one place at one time. I didn't make the rules up. There we go. So the quantum mechanical model uses a cloud model to describe where the electron's likely to be found. These clouds take on a particular shape based on where the electron with a specific energy is most likely to be found. So for example, there's like a 90% chance that the electron is somewhere in here. More about this next section. Quantum mechanics keeps the idea of energy levels. These are actually the rows on the periodic table. And it also adds sublevels known as atomic orbitals. These orbitals are referred to as S, P, D, and F. And again, more about that later. The shapes of the atomic orbitals depend on the energy levels. Okay, that's about it for this lesson. What are the big takeaways? Well, the Bohr model is not perfect at describing the atom, but then again, what is? It's a very important model, however, in understanding light and the movement of electrons between energy levels. And if we see here, now that I have a periodic table, we can see that the energy levels are located in the periods right here. So this would be the first energy level right there. The second period is the second energy level. The third period is the third energy level, and so on. Good. I hope you enjoyed that, and I'll see you next time.